Very happy to have Max Welling here with us today. Many of those who are in machine learning directly or indirectly must definitely know about Max. Max is a professor at University of Amsterdam, and he's also recently, this is my LinkedIn-based knowledge, director of MSR's lab in Amsterdam. And before that, I think you had in parallel some startup that you sold to Qualcomm, and you were at Qualcomm, et cetera, et cetera. But and Max has he's also been chair of, I think, NeurIPS at some point. And if you look at the variety of work Max has done is very impressive. And many of you may have heard of things like variational autoencoders, graph convnets, and so on. Those are some of the foundational topics that he's worked on, in addition to a large variety of other Bayesian stuff, of which he remains a long-standing expert. And there's many other topics of my personal intersection with Max's interest, but this is Max's seminar, so I don't want to derail on that. But very happy to have you here, Max, and the floor is yours. Thanks.
Thank you, Suvrit. I'm super happy to be here. Okay, let me see if I can share this. This works?
Looks good, thanks.
All right, great. Yeah, so today, let's see if I can get my, all right. So today I'll be talking about something that I got, I mean, a mixture of things that I was interested in already for a while, like symmetries, as well as something that I got interested in more recently, which is going back to science, and in particular molecular simulation, on which symmetries in machine learning are starting to have actually a big impact. And that's also the topic of the new lab at Microsoft Research in Amsterdam, that is all about applying machine learning to molecular simulation and understanding materials better. And I think there's a bright future for that topic. Now, of course, I have not done this work myself. I've done it in collaboration with many very bright people. And of course, the people you see here did most of the work. I was just supervising them. And well, this is just even a subset of all the people, but these are the people that I think impacted the work that I will be talking about today. And I will particularly highlight a few things which might be interesting. Of course, Taco has been instrumental in the symmetry development of symmetries in deep learning. And if you, he recently graduated, and here is his thesis that is actually a little Bible in itself on equivariance for deep learning. And so I highly recommend reading that. Maurice Weiler recently wrote a beautiful paper, you know, over 200 pages, I think, beautifully illustrated in, you know, of some of these pictures you can actually see also in the talk, of a sort of a mathematical foundation for equivariance in deep learning. And Mark Finzi here wrote a paper where he not only developed interesting theory, but also a very practical software tool that you can use, where you basically only have to provide the generators of the group and the representations that you like to entertain. And this code will then give you basically all the kernels that you need for deep learning. And that is a very low entry way of getting into equivariance. Okay, so I'll be talking about a few things here. Let's first do a little introduction in symmetries and equivariance. When I did my physics studies, you know, I don't know, 25 years or so ago, I got really fascinated by this idea that covariance, or writing laws of physics in such a way that they are valid for every observer, is a super unifying framework. In particular, I would say I think there's some chatter in the background. Maybe people can mute.
Yeah, for this one, just controlling it from here. So
Thank you. So in particular, there is a sort of, let's say, the laws of electrodynamics as written down by Maxwell. They unified electricity and magnetism by basically relating them by a observer where one observer moves with a constant speed relative to the other. So where one observer observes an electric field, the other observer observes a electromagnetic field or a magnetic field. And these can be transformed into each other through these different observers. And so by writing down your equations, not in this form, which is not really equivariant or not covariant, but in a way in 4 vectors with space-time vectors, everything looks exactly the same for every observer. Something similar has happened for general relativity, where basically, Einstein figured out that, in an accelerated frame, something for one observer that feels like, some force generated by acceleration really is exactly the same as gravity. So for another observer that doesn't feel it's an accelerated frame or think that it's an accelerated frame, interprets that force as gravity. So these 2 things are equivalent, and from that all of general relativity follows. And of course, even the standard model of elementary particles is organized according to these representations of groups. And you have leptons and quarks, and they all transform under certain groups. There are representations for certain groups. So there is some chatter in the background. Maybe people can mute those people. It will be very good.
Not only economic value.
Thank you. So there's group transformations that transform, let's say, the gluons into each other, and they form representations under certain groups, let's say SU2. Now in deep learning, we also have symmetries. For instance, if I have, let's say, a certain object, let's say a pathology slide, and I want to classify it into one of a number of classes, let's say somebody has a disease, yes or no, then of course, if I would rotate the slide, the label of that particular sort of disease would not change, right? And so we really want invariance in this case of the label under the symmetry transformation of the input. And so that sort of gave rise to this idea of equivariance, which is a more general notion than just invariance. It basically means that if I have some kind of object, could even be a manifold, but let's say let's say a plane for images, and I have some signal on that object. In this case, it's a drawing of a gecko, and I would filter it using deep learning. I would get some kind of filtered image of a gecko. But I can also rotate the the picture of the gecko under the symmetry transformation of the object. In this case, it's a rotation around this z-axis here. If I would first rotate and then filter, it should be the same as first filtering and then rotating. And that's kind of, for instance, the invariance would follow for class labels. There is a gecko, and the equivariance would follow, for instance, for segmentation, where you want to segment the gecko out of the background. You can argue that this idea has as an advantage that it will disentangle sort of the latent representations of your input. So in a neural network, you will build increasingly abstract latent representations of your input. And this symmetry or this equivariance builds some kind of structure onto that sort of these latent representations. They will organize them in so-called capsules. The term was coined by Jeff Hinton. And these capsules have basically the total activation of a capsule represents the presence of an object where the internal sort of state of the capsule could be, let's say, an angle of some kind, would represent the pose of that particular capsule or that particular object at the input. It also has other, so you can think of sort of symmetry or equivariance as disentangling somehow the latent representations, it's not quite the same as disentangling because these latent representations can still be highly correlated with each other, but at least it puts meaningful structure on those latent representations. It also helps with data efficiency because it adds an inductive bias onto your neural network. And that bias basically says that you impose certain transformation properties. And that means that you're going to share weights in your filters, and that would help you so that now you have less filters to learn, which means you can be more data efficient and learn faster. Of course, you see this very clearly in translation invariance or equivariance, which happens for CNNs, where in CNNs you just need a bunch of filters. These could be very small. Where in the version that is not equivariant, the multi-layer perceptron, you'll have to have filters which are n squared, with the number of input times the number of output neurons. And the final thing would be to say that the patterns actually created in equivariant layers, so the structures that you create in equivariance help the next layer to discover higher order structures in that. So you could imagine that if you rotate and all the pixels would randomly permute, the next layer would have a very hard time, finding patterns again in that data, especially when they are themselves trying to be equivariant. But if you put the equivariance on it, then the next layer, if that's also an equivariant layer, is a much easier time finding that structure. Now, finally, one could also, one other nice properties of equivariance is that that symmetries are preserved under abstractions. So if you take an image and you rotate it, which is you move it on some orbit of your symmetry group, and if two of these faces, let's say, map to the same abstract face, then the two rotated faces will also guaranteed map to the same object now here, which is, you could think, a rotated abstract face. So under these kind of contractions, you also, the symmetry sort of is preserved. Okay, so more mathematically, what we want is some kind of commuting diagram. If we first apply a filtering and then a symmetry transformation, we want that to be the same as first doing the transformation in the original space and then doing the filtering, right? So this would be first translating, then filtering, or first filtering, then translating. That diagram should close. Now, to make the point that this particular transformation here doesn't have to be the same as this transformation here. It is the same for translations, but not for rotations, is made in this illustration. So I have an image, and here I rotate the image. So this is the actual operation that we do when we do the filtering. So instead of just a normal convolution, we do 4 convolutions, but we rotate the filter and then store them in 4 different channels. So that's what's happening here. So I take the image, I sort of have 4 filterings, but with rotated filters. And so if the image is upright, I get 2 detections on the eyes and 1 on the mouth here. We call these 4 things, we call this an eyes capsule. And so you see now that the total activation of this capsule tells you something about the presence of eyes, where the actual internal angle or the internal activation tells you something about the orientation of the eyes, right? In this case, 0 degrees, in the mouth, 0 degrees. Now, if I rotate, then these 2 get activated. And so now I see that not only do I get a rotation of the activations, I also get a shift permutation in these capsules. And so now you see that the transformation in this part of your space is different, more complicated than the transformation is in the input space. So in Y space, it could be a different transformation than in the X space. Now you might think that CNNs are actually equivariant under rotations, but they're not. So here's a nice illustration by Jan McCunn a long time ago. You see under translations that the filters beautifully translate, but under rotations, they also change. They not just rotate, but they also change. And here you can see it similarly for a rotating Eskimo. This is a normal CNN that changes under rotations if you stabilize the picture, where the one that is sitting here, which is Daniel's actually harmonic network, is much more stable and invariant. Here's another one. This is a different breed of of equivariant neural nets developed by Taco Koa in 2017. We call them steerable CNNs. And in steerable CNNs, instead of discretizing your continuous symmetry group, you don't discretize it, but you do some kind of Fourier transform, and you throw away the high frequencies and you keep the low frequencies. And it turns out you can still build these sort of fully equivariant neural networks. Here you see one of these equivariant neural networks, where this is a scalar feature field with a single scalar value, and these are vector fields. So they are, you know, each pointer is a vector representation, so a feature vector that is vectorial. And you see that under rotations of the input, you get the right type of transformations of the latent representations, the hidden representations. Here it looks more complicated, but then if you stabilize it, these transformations, then they are completely invariant, and that's what you need for equivariance. Okay, so I already mentioned this, so I'll skip it. That's the code by Mark Finzi in the paper that you could use to start working on the problem. I also very briefly want to mention that we also know how to generalize these concepts to arbitrary manifolds. So in arbitrary manifolds, you're stuck with a little problem, which is that if you want to share the parameters of a kernel between here and here, you can't really, because well, it's hard because if you want to sort of transport your kernel from here to here, it turns out it almost always depends on the path that you take. For a Möbius strip, this is most clear. If you rotate it around, the chirality of your basis, your frame changes, and here on a sphere, basically you get an SO2 sort of rotation of your frame. Now you can fix all that by assuming that everybody has their own frame, using these sort of equivariant transformations and figuring out how to transform one result into the other result, basically. You have to read the paper for that. So now we're gonna go to graph neural networks, which is in a way also belongs to the topic of geometric deep learning, because now the sort of the input is also non-standard. It's not a line, it's not a plane, but in this case it's in our graph. So here's the graph. Now you can think of a normal convolution really as a message passing algorithm. It's very useful to think of a convolution as message passing. So if you think of multiple of these feature vectors here, so not just one blue plane, but many blue planes, and then at one pixel, you look at the values, you know, across all these planes, that's a feature vector that will be sitting here. So that's a vector. And now you can think of basically a convolution as multiplying that vector by some matrix W, and everybody uses their own matrix, including yourself, the message to yourself, and then you add everything up in the center, and that's going to be the new value store, and then you apply nonlinearity. For graph, this doesn't really work, and so in 2016, Thomas Kipf and I were thinking about this problem. How can you actually make sure that on a graph you can also meaningfully, you know, do message passing or convolutions? And here, if you think of it as message passing, it becomes actually quite clear, because so you cannot rely that the number of neighbors is the same. You cannot rely on the fact that the neighbors are ordered in any particular way. So what you really want is that if you would say reorder these guys, let's say this guy would move here, and so then you would reorder them, you would still get the same result in the middle, right? Because if you wouldn't, then this result would depend on in which order you process your neighbors, which is really undesirable. So the obvious thing, which turns out to be one of the simplest things to do, is to just use the same matrix here for all of your neighbors. Now, slightly more general idea is to use not just sort of this multiplied by a matrix, but a general nonlinear function between the feature vector here, the feature vector here, and maybe some information living on the edge. You compute sort of a nonlinear function, could be a neural network of these things. That creates a message that's going to be sent from here to here. So So it's now, instead of linear, it's going to be nonlinear. Then you collect all the messages, and then that gives you sort of one new vector here. You combine that with your feature vector at that point, and you combine it with you know, maybe with some fixed information on your node, and that again push it through nonlinearity to get the feature vector at the next layer. All right, so that's a more general way of, you know, more general message passing way that is still, you know, invariant, or, you know, under, you know, changing the order in which you process the neighbors. And the point is that if you do this everywhere, then in fact the total function from the graph, you know, to the graph is going to be equivariant, which means that if I take this one and I, you know, flip the labels for these two nodes around, then at the final output of my graph neural network, I will also flip the values, you know, of these, of the outcome of the neural network around. Now, why I'm interested in this, I'm interested in this also because I want to simulate molecules, and a molecule can be represented as a graph. Somewhat obviously, there's the atoms, and then there is the atom. You know, the edges are basically the covalent bonds between the atoms. And so what I would like to do is compute the dynamics of this particular molecule over time, right? So what, you know, that's called molecular dynamics. So that's basically to say, you know, if I would let this particular molecule relax, then there's all sorts of forces here. So, you know, these atoms repel or attract each other, you know, and there's forces between these, and there's rotational forces and all these kinds of things. There's maybe also other atoms or, you know, solvents that would hit it, you with some random force applied to it. And so you would like to sort of relax this molecule in its lowest energy state. The way to do that is to basically compute these forces on these atoms, and then just use Newtonian dynamics. Basically say, you know, the derivative of x is v, and the change in v is given by minus the gradient of some potential, but the potential comes from all the other atoms in the environment. But the most important part actually is the electrons. So those apply one of the most, you know, the largest forces on these atoms. And in order to compute that derivative, you actually need quantum mechanics. And here you typically get stuck, because it turns out that modeling these electrons using quantum mechanics is worse than NP-hard, or it is NP-hard, but it's in some quantum class. And so on a classical computer, it's pretty hopeless if you get into the hundreds of electrons. So you will have to do all sorts of approximations. If you still want to do this classically, of course, there's maybe going to be quantum computers, and quantum computers could actually help us with computing these particular electronic forces. Now, why are molecules so interesting? Why got I very interested in it? Well, first of all, from a philosophical point of view, they basically build up everything you see around you except for light and gravity, and some other nuclear forces, and maybe some things like plasmas. But most of the things that you can touch are, you know, built out of molecules. Yet we can only really simulate these molecules if they're very small. And so there's a lot to be gained here, because once we do understand molecules, there's a lot of interesting applications both in healthcare and environmental and climate sciences. The most obvious one is drug discovery, right? If you understand how proteins fold, how proteins bind to other proteins, you can start to design drugs and vaccines from in silico, basically in your computer. For the energy transition, important is photovoltaics, which is turning light into energy, and also at the interface, molecules play a profound role. 20% of our energy we waste basically through friction. So 20% is quite a bit. And so building better lubricants can help there. Catalysts are important for a number of things. For instance, turning water into hydrogen and oxygen, which has to go over a free energy barrier. But you can build catalysts to make that process and more energy efficient. They're also important for nitrogen fixation. So building, developing fertilizers or producing fertilizers, that's a very carbon wasteful process. And so taking better processes to generate nitrogen is definitely should be very helpful for the environment. And then in terms of biology, at some point we would like to understand all the proteins in a cell and how they interact. Now the key challenges that we need to solve are more accurate simulations, which means that we really need to approximate quantum mechanics better so we can understand the forces better. And that means that we can do dynamics better. We need faster simulations because nature wiggles on a time scale of femtoseconds. That's millions of a billions of a second. And we need to accelerate that, many orders of magnitude to see anything interesting in, your lifetime in a computer. And so you will want to accelerate that in silico. And finally, we want to do much larger scale simulations, hundreds of millions or billions of atoms, rather than tens or hundreds of atoms. And of course, there we need, coarse graining methods and all sorts of other approximations to make that work. Now, I'm just going to talk a little bit about this work. It's a couple of slides that is natural graph neural networks. I was just saying that in normal graph neural networks, you're sort of stuck with this isotropic convolution, which is very limiting in a way. It's still surprisingly powerful if you think about it. It works. It can solve, quite interesting problems, but it doesn't have to be isotropic. And I'm going to very briefly try to explain why. But really, the paper to read here is Pim de Haan's Natural Graph Neural Nets. So what we really want from our graph is permutation equivariance, right? So what we want is to say that if I take my graph and I permute it, sigma is a permutation of the nodes of the graph, and then I convolve it, I process it somehow, that should be the same as first processing the original graph and then doing the permutation. And as I said, we want something that's not as limited as treating all your neighbors exactly the same. So really what we want to do is if I have some little graph here and I have assigned some nodes to it, and of course this could be a much bigger graph. And now the symmetry operation isn't a rotation or anything. The symmetry operation is a permutation of the node labels. So I'm going to relabel things a little bit here, which means that so now I'm going to look at, let's say, node number 1. And node number 1 has a representation that is not just a scalar, but is a vector. And is a vector that's organized around, the structure around it. So let's say it has some vector here. This is its neighborhood, right? Or in this case, the entire graph. And it just has these this vector assigned to it. Now, if I permute, then what I want is that the vector also permutes with it. Now, if I'm going to process this vector in some kind of neural network with some kernel that depends on this particular graph representation, I'm going to process it into something new. Let's say this is the new vector that I'm producing. Then what I really want is that if I, act with my kernel on my permuted vector, which gives me a kernel for G prime for this permuted sort of graph, then I want the outcome to be the permuted version of this, right? It feels fairly trivial, but it's not all that trivial to make it happen. So how does that relate to a global graph isomorphism? Basically, if I have some graph and I'm going to permute globally the value, the labels of the nodes, how can I make sure, how does this sort of property result in a global equivariance, right? Because I'm now gonna, at some point, I'm just gonna do this locally. I'm gonna say I'm gonna send a message from here to here, right? And I'm gonna send a message from here to here. So this is sort of a local operation. But what I'm going to demand is that if I use a kernel here for this particular graph, and I go to somewhere else in my graph, let's say here, so this would be the mapping, then I would like my kernel here to be the same kernel here if I map this point to this point, and if I map this point to this point, etc., etc. So I want this kernel to be the same for both of these situations, but sort of permuted. The other one is if you have a permutation inside, where let's say in this case, I would map this guy to this guy and this guy to this guy, then I actually have a symmetry. So the graph looks exactly the same. So if I write down the incidence matrix, it's exactly the same incidence matrix. And that means that would result in some kind of constraint on that kernel that I'm using for processing, this particular subgraph. So if a graph has a symmetry, I will have to put a constraint to make sure that if I relabel these two things, I will still get the same result. And there is some weight sharing going on in this graph for every local neighborhood. I need to use the same kernel or a permuted version of that kernel. So those are the two things I need: weight sharing between isomorphic neighborhoods and invariance if I have some kind of symmetry. And if you do these two things, basically, then you can show that these kind of local message passing updates, which are not isotropic, will result in global permutation equivariance. Note that these messages can be non-linear; they don't have to be linear, and they're local, so they can be operated distributively, so they can be faster that way. Okay, the next paper I want to talk about is, now that we have some way of building in equivariance under permutations, I also want equivariance under rotations, because after all, a molecule, if I rotate, will have the same properties, right? And so illustrated here is, I have some graph. Let's think of it as a molecule. There is some invariant properties. These are the features, the scalar features of these nodes, and then there is some forces or some vectorial properties that belong to this node. Now, if I would first process it, I'll get something like this. So now everything changes because this is just a sort of a layer of a neural net. But if I rotate it, then of course this got, this x4, let's say, goes all the way here. So x4 goes now here. The scalar features will remain invariant because they're scalar, and the vector features will rotate beautifully as they should under rotation, right? And now I want this and then this to be the same as, first filtering and then rotating. Now here's a very detailed way of writing messages that precisely fulfill this. And this is one of the simplest graph neural networks that has that property. There's a paper by Victor Garcia Sotares and Emil Hoogboom. And the idea is here that we compute our messages M, again, as before, based on the feature vector on the receiving node and the sending node at that layer, but now also on the invariant on the rotations, which is the distance between the positions of the two vectors. So I can stick that in. Now this is an invariant message now, it doesn't change under rotations. Then I'll update my velocity vector V, basically by a linear combination of the original, or so take the original vector V plus, let's say, the difference vector between xi and xj. So that's a vector and that's a vector. And I'm multiplying it by scalars, so that's still a vector. Then I can update my x. I can aggregate my messages, which is also invariant, and I'll do a final update on h, again, using invariance. So all of this, all the m's and the h's are invariants, and the v's and the x's are vectors. So they behave covariantly. And so this is one of the simplest versions. Here is a more sophisticated version, and I will go over this fast. I'm just going to say, you can read the paper, and it is It is based on the idea of a transformer. Again, you're sending messages between neighbors. There's keys and values. You take in a product. You compute attention. The attention is invariant, but the value is a vector, and that transforms covariant like a vector. And in this case, the representations are not just 3 vectors, but they can be arbitrary higher order representations of the rotation group, which you build out of harmonics, spherical harmonics. There's a lot of details, and you'll have to look them up in the paper. This paper, Steerable Equivariant Message Passing on Molecular Graphs, has even is sort of an even further development of that idea, again built on spherical harmonics. It introduces this very general idea that the message is just a equivariant neural network, but message. So you take the features on one side, one node, you take features on the other node. These are representations under the group. You take other invariants, and then you just take a equivariant multi-layer perceptron or an equivariant neural network to then compute your messages here, which are then again transform as vectors. Again, this is a very general formulation. You would have to look it up. As I think it's one of the most general formulations of equivariant graph neural networks today. Okay, and here's a visualization of how that works. So these funny blobs are visualizations of spherical harmonics. I guess this directionality, so it's really a function on a sphere, but they are visualized like this. And this is what you see as you move through the layers of a neural network. You see these things transforming. And if you rotate this particular molecule here, all of these things will beautifully rotate with the actual angle. Okay. Then I'm going to move on quickly to a somewhat different topic, but not completely unrelated. This is now trying to do the inverse of what we just did. We just built models for, let's say, you give me an input neuron, an input molecule, and you're going to predict that all sorts of properties of the atoms or of the entire molecule. Now I'm going to try to do the inverse, which is you give me a data set of lots of molecules, build for me a probabilistic generative model that can generate molecules that look like the molecules in your data set. You could imagine that this is very useful because especially when you can do conditional generation. So then you can say, as a chemist, you can say, give me a molecule with these particular properties. Let's say it binds to this nasty virus. And so now generate candidate molecules that could act like drugs. Now, I think this is just the start of an exciting field, and there's only a couple of papers out there that start to do these things. But one of the sort of most useful things to do is to think of this as an invertible flow model, a normalizing flow model. So you start in some space using a very simple distribution, and then you have some forward set of transformations which are invertible that would sort of transform this cloud into the density that you're interested in, which is this. And since it's invertible, it turns out you can write down the log likelihood of this problem and easily backpropagate through it. Now, what we did is basically exactly that. We took as input now a bunch of molecules, including their types. And then we had a normalizing flow, which is based on this, this particular equivariant neural net, this one. So based on this particular equivariant neural network, we computed basically the flow. It's an ODE flow that would then assemble from this sort of mess here, would assemble a viable molecule. And of course, you would train that. So here's, it's hard to understand so quickly, but you first have to lift all the discrete features, which are the types, into some continuous space. The process is called dequantization. Then you have to integrate using your ODE. You have to integrate forward the transformations of the continuous variables that you have here, including locations as well as types. And then you map them to a Gaussian distribution. And then there's also a distribution for the number of atoms that you're going to generate. Anyway, if you do that, you're not supposed to really understand what just happened. It's too fast. But if you do that, you get this beautiful model that's equivariant under rotations. Now, what does that mean? It means that if the probability of generating a molecule in a particular orientation is mathematically equal to the probability of generating that molecule in a rotated orientation, right? Is built into the system. So here is, the mass in Gaussian space, different types, and then here it gets assembled into a reasonable molecule using the flow. And you can also, and then you can rotate it. It has the same probability. Okay, so the final thing I want to talk about, we're running a little bit out of time, I think, but the final topic is something I'm also very excited about, which is solving PDEs with graph neural nets. So these graph neural nets are starting to become a very versatile tool for scientific computation. And this is sort of maybe the overarching theme of this talk is graph neural networks are very general, or equivariant graph neural networks are a very general tool that will find applications in all sorts of scientific computations. And here's another one that we started on, and other people have also done some work on this. But we model it with a graph neural net. So we look at a PDE. So PDE is some vector field U over space X and at time t. And we take the time derivative of that vector field as some function of time, space, the values U, and all its derivatives. There is some initial condition which says that the initial vector field is given by some function that you know, and there's some boundary conditions as well. And there's a special class of PDEs which are basically follow this form, where you now have the divergence of some flux. And basically all this is saying, if you can sort of recall your Gauss-Bonnet theorem, I think it's called, is basically saying that if you take an arbitrary piece of volume, then the amount of stuff that goes into this volume minus the amount of stuff that goes out of this volume is the change of stuff inside this volume. And that sounds almost trivial, but of course it's saying that there's no sinks or sources inside any volume where stuff gets created or destroyed. Now, the type of solvers that we use go as follows. So we have our particular vector field at time t, and we have some mapping A and a dt, and then this mapping A is going to be sort of our GNN based model that maps the values of U to some point in the future. This is exactly what you would expect. Now, the loss function is also what you would expect, which is basically saying, let's use some very high resolution, expensive solver to create some solutions of the PDE. And now let's take the value of U at some time, apply your forward map A, and make sure that these two values are the same. And of course, you have to sample UK and UK plus 1 in some way. And I'll have to say one more thing about that maybe. You have to make sure that actually you add some noise in order to make this robust. There's this idea of temporal bundling to make things fast, which is to say, don't just predict one time slice at every time, but predict a whole bunch of time slices at once, and that goes much faster. The model that we use is based on a GNN again. It's not yet equivariant, but we're working on it, and the mathematics works out to be very beautiful. There's a lot of symmetries in these PDEs, surprisingly, because now you also have the vector field U that is involved in the symmetries. So the architecture is as follows. You take some kind of sequence of U's in the past, from the past to now. You first map them one by one through an MLP to get some feature vector. This goes into a graph neural net that sends messages for a couple of layers, and that goes as follows, very similar to the one that I described. Depends on the difference of the feature vectors, depends on the difference of the U values, depends on the difference in space, and it depends on the parameters of your PDE. and then you do an update on F. So this looks a lot like the usual message passing scheme that I described before for your GNN. And then finally, you take your outcome and then you do a CNN to sort of smooth the values a little bit. That will give you an update for your U, and that goes back into here and this one, and you cycle through this, you know, iteratively. And you, of course, you also back propagate through this iteratively. You know, so there's one tricky part which is to do with noise. So you will accumulate error if you do this, and in order to make it more robust, you want to make sure that you train it on data that has already accumulated error. So you want to sort of simulate the process of accumulating error and using that as your input to the distribution, and that makes the whole thing a lot more robust. So here's some results. So this is ground truth, this is X, and this is U, and the color is time. So you start with the blue curve and then you move to the red curve. And here's a sort of a, if you have lots of points in your graph, so you know, higher resolution in your graph neural net, and here you go to less and less resolution. What you see is that even these shock waves that are forming in the Burgers equation, even these shock waves are beautifully reproduced in these graph neural network numerical integrators. You can even do something cooler, which is you can parameterize sort of an envelope of PDEs, you know, including Korteweg de Vries, Burgers equation, and heat equation. And there's just 3 parameters that you can use to sort of interpolate between these. You can then train on one set of parameters or some distribution of parameters, and on test on another set of parameters, and you can actually generalize between, you know, these families of PDEs, which is kind of cool. Which I think is even cooler is you could now start with just showing this data and then back propagating through this whole thing to actually learn the parameters of your PDE, which would mean you can sort of find the right PDE that describes your data from this process. We haven't tried that yet, but that's something for the future to do. Here is another experiment with Navier-Stokes in 2D. Here's the ground truth over time. This is the prediction over time from the graph neural net. Okay, so let me wrap up then. I think we're at a very exciting time, and the reason is that there's a lot of things coming together in scientific computation. There is, of course, the fields themselves, like condensed matter physics and computational chemistry and molecular biology, who are advancing at a very high pace. Think of genomics, for instance. Then there is the modeling sciences, including computational science or high performance computing, machine learning, deep learning, and quantum computing. They're also advancing very fast. And that can help us really improve modeling for these domains. And then there is pooling from a number of interesting and societally very important domains, such as health. So you could imagine that you know, we could develop new vaccines much faster using these technologies. And I think I saw even an article that MIT people had even used machine learning to develop new antibiotics, which were resistant against bacteria. No, they were still working against resistant bacteria. And for instance, immunotherapy for cancer. So these are all super exciting applications. And then also, I think there's going to be a lot of investment in energy transition and sustainability. You can think about carbon capture applications, which is going to be obviously a huge deal in the future. Hydrogen production, clean fertilizers, and biodegradable plastics. And yeah, I think that's about it. And I'll stop there and see if there's any questions. Thank you very much.
Thanks, Max. There is one quick question in the chat. Can you access it, or should I read it out for you?
I can access it. Let's see.
Okay.
What is meant by robustness and how we measure it? Also, how can one be sure how much noise is enough to make the data such that the model we are training on is robust? Right. So maybe I'll just explain a little bit more what we did. But the issue is, of course, that if you use a PDE and you integrate it forward, then you'll start to accumulate error. And if you just use the data from a high resolution, expensive PDE solver, where this accumulation of error isn't happening, then you're not really training on the distribution that you will experience in the real world. So what can you do? So you just take some point in your sort of high, from your exact solver, your high resolution solver, highly accurate solver. Then you integrate forward a little bit using your approximate solver, accumulating some error. You stop, so that has a different distribution now. And then you try to predict again the real solution that is provided to you by the highly accurate solver. So this means that you will then try to predict from a distribution where already the error is accumulated back to the ground truth that you would like to predict. And that trick helps huge amount in actually making the PDE solver more robust, and with this I mean accumulate error less quickly.
Interesting.
Any more questions?
There is one more in the chat.
Oh yeah. So this is Ahmed Berami. So thanks for a great talk, Max. What do you expect will need to happen for ML to be impactful in more complex systems where we don't even know the physics that govern the medium? Yeah, obviously very interesting question. So the PDE gives you a little answer there. So I think these PDEs can certainly, so you can think of building a very large library of terms for your PDE, and then doing some inference on, you're trying to integrate your PDE, or you're trying to train it to solve your PDE. But then you can also basically backpropagate to the parameters of your PDE to pick out the right ones which describe the data that you're seeing. Now, there's also been some great work by people who, maybe even from MIT. I'm blanking on precisely the name. I think it was Cranmer was his last name, not Kyle Cranmer, but the other Cranmer. But anyway, so where you first use a graph neural network to sort of do, try to do prediction, and then you have some way to extract the symbolic mathematical equation that describes best the sort of prediction that you found using your neural network. And that also seems to be working quite nicely, and there's also quite, of course, some improvement that can be done there. So there is some future, I think, in looking just at a lot of data, trying to model it, and then extracting the bits and pieces that are sort of that we know describe physics very well, which could be PDEs or other symbolic sort of equations, typically maybe ODEs or something like that, or maybe even constraints, something like that. Implicit equations.
Additional questions, anybody? I just wanted to ask, I had several questions, Max, but I just wanted to ask a very high level kind of question on what are like the key computational concerns that you have encountered in this broad spectrum of work that you talked about?
Yeah, sort of. I think if you're concerned about the molecular simulation, then it's clearly the quantum mechanical part. So trying to simulate quantum mechanics is well, it's NP-hard, so you have to do approximations. And if you talk to the chemists, You know, they're all using DFT types of calculations because
Yeah,
that is,
yeah.
yeah. So that's an approximation that's still sort of okay-ish in terms of the number of electrons. I think it scales as n cubed or something like this, but still give you a reasonably good approximation. But you know, that's basically where all the computation goes, I think. Now, more generally, graph neural networks are, you know, very efficient because you know, you can run them distributively, right? There's a local message passing algorithm, so you can really run things, you know, distributively. You can amortize over different machines. So, I'm not so worried about that part. Now, the equivariance part is if you use things like, okay, so here's another one. If you do graph neural networks and you apply it to a molecule, if you want your graph to be fully connected, which means that every atom interacts with every other atom, then again, it scales as n squared, and that's typically for larger molecules also not really doable. So you would like to only look at your neighbors, but then if you only look at your neighbors, you don't want to, you know, you want a very rich representation of your neighbors. So not just a single vector and some scalars. You want maybe some higher order representations of the rotation group. And so then you get to, you know, these spherical harmonics, but then spherical harmonics are, of course, a little bit more computationally expensive. And so there's a trade-off there again that you will have to make. Yeah.
Interesting.
There's one more question here. Can
Yeah.
you read it? Yeah.
Yeah, sure.
So Amanyalan. So thank you so much for the talk. Regarding PDE solving, could you elaborate a little more on how the graph was constructed in the sense of what the nodes and edges represent and what their features represent? Right. So actually many, that's a good question because many people ask that question and sort of in my head it's clear, but it's not all that clear apparently. So the thing is that the edges actually represent basically the spatial grid. So in a PDE, every node will have to look at its neighbors because you're processing derivatives of a field, right? And second order derivatives of a field. So you have a U vector that's a function of X. And in order to compute the next values of that vector at the next, you know, time step, you will have to look at the local neighborhood. And so the graph neural network basically looks at the neighborhood by receiving messages from their neighboring nodes in the spatial grid. So that's what the graph neural network basically does for its updates. Of course, you learn how to, you know, how to do the updates, how to integrate things. But of course, there's a lot of symmetries, which is really exciting. There's actually a huge number of symmetries in these PDEs, and it's not so hard to include them. And so we're now working on how to include these symmetries in these updates as well. I think that's going to improve the performance further. Let's see. So how do you view the differences, trade-offs between the GNN PDE architecture you described and other non-GNN based PDE architectures, e.g. Fourier neural operator or deep ONet? Yeah, so I think there is actually quite different. I don't know precisely how these others work in detail, but I think what they do is they have a different predictor for every time slice. So they have one neural network for, you know, type T and for T+1 and T+2. So they have different operators for all of these that they train. So in our case, it's really autoregressive. So we really, you know, the next step depends on the previous step. So in our case, you accumulate in principal error that way, but it's also, of course, you can run it forever, right? It's not like, you know, that you can only run it for the times that you've actually trained this thing on. So there's different pros and cons, I think, and we compare it to the Fourier neural operator, I think, and it's, you know, I think we are faster, but, you know, but on the other hand, you know, both work fine, I think. So both are great ideas, I believe. Yeah, you can send more questions if you want, certainly. Yeah, so that's it. I think we're already 5 minutes over time.
Sure. Well, in case there's any quick question, this is your chance. Otherwise, just pause for 2 more seconds. Okay, seems like then we can conclude the seminar and thank Max again for his great talk and very informative session.
All right, thank you very much.
Thanks, Max.
Have a great rest of the day. Bye-bye.